Hello, and welcome to today's webinar, The Need for Resilient PNT Services to Ensure Safe and Secure Transportation Infrastructure, brought to you by GPS World Magazine and our sponsor of the event, Microchip. I'm Kelly Limpert from North Coast Media, Senior Content Marketing Specialist for GPS World, and I will be the producer for today's event. Before we get started, I wanted to let you know that today's webinar will be recorded. You are currently in a listen-only mode. A recording of this webinar will be posted to gpsworld.com/webinars and will also be emailed to you tomorrow. Now, at this time, I'd like to acquaint you with some of the ways you can participate during today's presentation. Please notice the Q&A panel on the left side of your console. If you have a question, type it in the panel's text box, then click Submit to place your question in the queue. We encourage you to ask and enter your questions you may have for our speakers during the presentation. We will address these questions at the end of the presentation during the Q&A portion. Questions submitted during registration have already gone to our panelists and may be covered during this presentation. If you experience any technical difficulties during today's event, you may use the same Q&A panel on your screen to submit your issue, and assistant producer, Mackenzie Schoner, or I will personally assist you. You may also learn more about our speakers by viewing their photos, bios, and email addresses in the panel located in the upper left-hand corner of your console. If you are logged into your social media accounts, you can share the webinar's title, description, and URL with your friends and colleagues using the Share This widget. Now, I'd like to turn today's presentation over to Duke Buckner, Head of Strategy and Business Development at Microchip Technologies' Frequency and Time Business Unit, to introduce today's speakers. Duke, the floor is yours.
Thank you, Kelly. Appreciate it. Thanks, everybody, for tuning in for a very informative webinar on PNT Safe and Secure Transportation Infrastructure. We have three noted experts in the PNT space with us today. First is Mitch Nairns, the Principal Consultant and Owner of Strategic Synergies. Guy Bunnell as a Security Technologist with Spirent. And Greg Wolf, Senior Product Line Manager with the Frequency and Time Systems Business Unit at Microchip Technology. During today's presentations, we're going to ask you to participate in some live polling, so be prepared. We're going to give you a question and some multiple choice answers, and give you about 30 seconds to answer, and then we'll review the results. And so I encourage you to pay close attention as we go through the presentation today. So first up is Mitch Nairns. Take it away, Mitch.
Good day to everyone, no matter what time zone you're in. We're going to do a lot of information in a very short time, test our time stuff here. So I'm going to talk about the need for robust and resilient position navigation and time in the transportation sector. But I first wanted to talk to you about some appreciation slides I put in here. The first one you're going to see is a day in the NAS. This comes from, I think, 2005. It starts around 1,700 hours on the East Coast, 1,400 hours on the West Coast. Take a look at how we move planes in the National Airspace System, and it's quite remarkable. Okay, so that was my first appreciation slide from many thousands of feet up. This one here has sounds. Listen carefully for when the wheels hit the tarmac, and then count the number of seconds before you realize you're on the runway.
Line 3.
Roger.
100.
Line 3.
50. 30. Speed brakes on.
that's just a view of the NAS from two different perspectives, vastly different perspectives, but it should give you an appreciation why position navigation and timing are so important. So before I get started, let's talk about some definitions here. I use the word robust and resilient. Robust is the ability to withstand or overcome adverse conditions. And resilient, coming out of the Presidential Policy Directive of 2013, is essentially the ability to prepare and adapt to changing conditions, and specifically to be able to withstand and recover rapidly from disruptions, including both deliberate attacks and naturally occurring threats or incidents. So we can all agree that robust and resilient PNT is the provision of PNT services that are strong, sturdy, able to withstand or overcome adverse conditions and recover rapidly from disruptions. So the next question, obviously, are what are disruptions? And for GNSS, disruptions are interference. And recognize that interference can be either intentional or unintentional, predictable or unpredictable, man-made or environmental, crude or sophisticated, or widespread and localized. And it applies to all the GNSS-provided services, whether it be position, navigation, or timing. Well, in 2013, like I said, there was a presidential policy directive, and the purpose of that was to advance this national unity of effort to strengthen, maintain, secure, functioning, and resilient critical infrastructure. And for its critical infrastructure, the U.S. said that they needed to maintain services and operations in the event of the GNSS interference event for safety and security, for maintaining a reasonable level of capacity and efficiency, and for minimizing economic impact. So this was 2013, 7 years ago. In 2001, the VOPI National Transportation Systems Center put out their report on GPS interference. So next year is going to be the 20th anniversary of that. So ask yourself, how far have we come and how far do we really need to go? For critical infrastructure, waiting for the source of the interference to be located and turned off is simply not an acceptable alternative. You have to be prepared. So how do we get there? Well, this is a slide I borrowed from my Homeland Security folks. The 20th century perspective, I'm a child of the 20th century, GPS was like the internet. It was wonderful technology, and there were nice people out there. Satellites in the early days were scarce, so you found different ways of working around the scarcity, including using pseudolights. And receivers had to do some interesting stuff to be able to provide position. And GPS receivers were seen as radios. In the 21st century, GPS is like the internet, but it's wonderful technology and threats abound. And since threats abound, receivers really have to be robust and discriminating. And receivers are really network computers with a wireless access port in mid-Earth orbit. So we need to implement best practices so that we get a 21st century solution in the equipment area, for installations, and for operations to address the threats that we see in the 21st century. So this year, an executive order came out, 13905, specifically entitled Strengthening National Resilience Through Responsible Use of PNT Services, and that came out this last February. And here are the three main points of the policy. First, to ensure that disruption doesn't undermine the reliable and efficient functioning of any of our critical infrastructure. That the federal government needs to increase the nation's awareness. That's really a problem. Many people are not aware of the vulnerabilities, despite reports and studies and tests and everything. And we've got to be able to ensure the critical infrastructure can withstand disruption or manipulation. And towards this end, the federal government says it's going to engage with public and private sectors to identify and promote resilient PNT services. And PNT services are the means by which you derive PNT information, whether it be a system or network or some other capacity. And the responsible use of these PNT services means that you understand, you're deliberate, you understand the risks associated with PNT services, the acquisition, the integration, and the deployment, and you do something about it so that you don't affect safety or security, you minimally affect the economy, public health, or other critical functions of the government. Because remember, Resilience means being able to come back from an impact. So for the aviation sector, safety and security come together, and that's what forms the resilience. And for the aviation sector, on the safety side, you've got the safe recovery of aircraft. Approach and landing is certainly the most risky stage of flight, phase of flight. You don't want to have any significant impact to either pilots or controllers. On the capacity and efficiency side, you want to be able to make strategic modifications of trajectories, and there's nothing closer associated with PNT than trajectories. Those are four-dimensional entities, and continuing to be able to dispatch and receive planes in areas that are affected by GNSS interference. So PNT resilience certainly needs to be a combination of ground-based infrastructure as well as signals in space, but also the user end, the receiver capacity, your installation, your antennas, and everything else have to come together in order to provide you with a resilient PNT solution. So I want to concentrate about time, because time is that utility that everybody seems to use and not understand how important it is. Some years ago, Homeland Security came out with this list of critical infrastructure sectors and just noted that 15 of the 18 at the time specifically used GPS for time. And there's the transportation sector that we're talking about today. Many users do not even realize they're using GNSS for time and frequency. It's sort of like that people will understand that the power grid has issues, and they'll buy engine generators if they have critical functions in case the power grid goes down. But they don't understand that time is this utility that if they don't have it, they're also suffering possible failures. So the sources of time, GPS, it's great, 10 nanosecond time accuracy, 1 times 10 to the minus, I think it says 19th there, 16th there, for frequency stability. WWVB is still being broadcast in this country. I know other countries have other time broadcasts. And then you have the Internet Time Services of NTP and PTP, and those provide specific levels of capability. And cesium clocks are good, for 10 nanoseconds, and certainly will maintain your stratum 1 timing as long as the tube is still good. Rubidium clocks give you microsecond. And in fact, I've got to point out, when I did this drawing originally, you'll see where PTP shows up. And certainly in recent years, the efforts that people have done in terms of using fiber to distribute PTP time, that little rectangle has moved significantly to the left. You can get much better time with PTP if you do it right. In terms of user side, there's always the manual time stamping where you have to keep the legal records to the nearest second, but everything is moving to more precise time needs, even the financial markets, because you can drive a truck through a millisecond, and you're going to be able to drive a truck through a microsecond as well, and you've really got to be careful about that. But some of the things, weather data stamping, automation, runway visual range, when you're fusing different sensors together, you need to make sure you're doing it in the same time frame, or at least take account for that. Maintaining 3-mile separation. The ASTERIS time stamping. ASTERIS is a European radar standard that's being accepted that requires microsecond time capability. The power grid, network time sinks. And if you're using it to determine your position, you need nanoseconds. A nanosecond is a foot, so how many feet are you willing to throw out? So certainly precise and high integrity time is needed. In terms of guidance, DHS came out with this document. It's available there. But their recommendations are: know your system, know the timing sources, know your users. Regularly update your system and document and test your systems and sources. Diversify your time sources. 2 GNSs do not make for a resilient time source. It's amazing that some folks actually believe that. And detect and address the problems that your time sources have, because they're not perfect. And in summary, you really need to think about this need for robust, precise time and frequency, again, strong, sturdy, able to withstand and overcome adverse conditions. You should never use GNSS as your primary or sole means of time, and there really needs to be this paradigm shift. People have talked for years about GPS timing receivers backed up by oscillators. Your time source really needs to be an ensemble of oscillators that can be smartly disciplined with GNSS timing receivers. And if you do that, you're going to be able to put yourself in a much more resilient position. Also recognize if you're a fixed operation user, knowing that you're not moving is a good sign of whether somebody's messing with your GNSS signal. Anyway, tried to do that in a New York minute. Back to you, Duke.
Thank you, Mitch. Very informative. Okay, so that brings us to our first poll question. So get ready with your mouse and we'll ask the first question. Is your primary use of PNT, is it position, navigation, or timing, or all of the above? So select one answer, the most correct answer for you, and hit submit, please. I'll give you about 20 seconds. Position, navigation, or timing, or all of the above. Okay, all right, let's see how the audience responded. All right, so about 10% say position only, another 17% navigation only, a large percentage timing exclusively, and another large chunk with all. So, okay, well, thank you for your input there, and we'll hand it over to our next presenter, Guy Bunnell from Spirent.
Hi, thank you, Duke, and good evening from the UK to everyone here. Well, today I'm going to summarize the main threats to GNSS signals and talk through some of the real examples we've come across in recent years and the impacts that we've seen, observed, or reported from them. In fact, Mitch started to outline some of the threat classes in his presentation. We'll see that unexpected system responses often occur, and they highlight the need to understand your GNSS-dependent systems. The need for robust, precise timing and positioning data in safety, reliability, critical applications in transportation systems is really very, very clear. GNSS signals are vulnerable to a variety of mechanisms, as this diagram shows, where they're vulnerable to spoofing, interference, GNSS segment errors, multipath, atmospheric effects, and also all of these things obviously can cause serious disruption to GNSS signals, but in addition to that, we also have the plethora of cyber security attacks that all connected systems face today. And these are the sort of things that we have to face. The next few slides are really an attempt to describe some of the main sources of GNSS vulnerability, some of the main threats on the threat surface, if you like, along with the circumstances that you might encounter them and the frequency with which they might occur, along with the possible impacts on a user. Now, I'm not going to go through them all in detail, but they're there for you to read afterwards in the material. This particular chart is focused on the naturally occurring threats, such as atmospheric threats, scintillation, solar storms, obscuration, which is a very common problem in installed systems, and multipass, which again has often significant effects in urban canyon type environments. So there's even here on the natural vulnerabilities, we have a lot to cover. Obviously, we're going to be looking at in a bit of detail at more man-made type incidents. And moving on to man-made vulnerabilities, as well as jamming and spoofing, which we'll hear a lot about later on, I've also listed here poor installation. And you might say, well, that's not really a vulnerability, but I've put it here because we see a lot of instances of this in the world, unfortunately. It's one of the byproducts of GPS becoming so ubiquitous, is that there are quite a few people out there who think, well, We just have to plug an antenna into a GPS receiver and everything's going to work okay. It works in my car. And often it doesn't. Also worth noting, I think, is that when we talk about GPS jammers, we often think or believe that GPS jammers just take out the signal or deny GPS reception. In fact, all the evidence and all the facts out there show that they can degrade it too, and often do. And this is the gray area where range information is affected. It's where a device can actually output hazardously misleading information without any indication of being jammed. It's an area which isn't often talked about enough. Sometimes when a receiver is operating in that gray area, the information it's outputting can actually look very similar to the symptoms of a spoofing attack. And often the receiver's GNSS performance degrades well before the receiver stops tracking satellites altogether. Finally, I'll just talk about briefly on RF interference that's unintentional, user errors, cyber attacks of a non-RF type. In the GNSS industry, we often focus on the RF or electronic warfare type of attack. These are the ones that gain the headlines and get in the press all the time. But, as Mitch said earlier, our GNSS systems and devices these days they're connected devices. So they're vulnerable to all of the network information security types of attack, man in the middle, malicious modification of code on embedded devices, denial of service attacks using ARP, that's address resolution protocols, and the NMEA 183 output of GNSS devices, the protocol, is unencrypted, so again, can be a relatively easy target for a hacker. Moving on to some real-world examples, some of these threats in September 2017, in Europe, Russia had been conducting some military exercises, and there were reports from northern Norway of problems with GPS reception, and these problems were mainly noticed on commercial flight operations, although I've heard one or two reports of ground systems, surveying systems to be specific, being affected too. Also in the UK, we found a ring of criminals were convicted who were using GPS jammers quite widely in order to prevent them being tracked. And of course, you wonder how much collateral damage is caused by that system. Also, in India, car thieves have been caught using GPS jammers when they steal luxury cars. And I had an experience actually in London a couple of years ago when I had to flag down a taxi to take me to a railway station. And in the cab, I noticed that the cab driver had a cigarette lighter jammer plugged in. So I actually asked him what he was using it for. And he actually said in an awesome London accent, those Uber drivers, it makes it difficult for them to meet up with their fares if their GPS is jammed. So there you go. There's a motivation to use jammers in the real environment for you. In 2016, there were reports of strange problems in St. Petersburg, and also Moscow had similar sorts of problems. Car sat-navs showed locations near a commercial airport when the actual location was in the city center. In September 2017, the US issued a maritime advisory, which advised of incorrect signals in the Black Sea. And the photo in the bottom left-hand corner actually shows one of the sat-nav systems on a ship. It's a photo showing the position that was recorded by the ship, which is on land, and the actual position of the ship, which is about 20 kilometers away. Over 130 ships were affected. Recently, the US have just renewed and extended that MARAD, and they're warning of multiple worldwide instances of GPS interference in the central Mediterranean, Persian Gulf, and multiple Chinese ports. So you can see that this is an extensive problem. And talking about those multiple Chinese ports brings us to the crop circle spoofing. In 2019, a very odd set of incidents started to occur. Many vessels experienced mysterious position spoofing. In other words, the ship's position was seemingly shifted to a point on the circle near various points on the river. It's a real mystery. I mean, no one's observed anything like this before. It's certainly some kind or kinds of deliberate spoofing. All of the reported symptoms seem to point in that direction. But you have to say there's a lot we don't know, and the motives are very uncertain too. It's great for speculation. It's a great story for the press who have actually enjoyed talking about it. I think the main point is, as a user, you don't really want problems with your navigation or timing system causing these mysteries or speculation in the press. And also this incident highlights the risks of collateral effects. Many of the reported problems I've talked about today have come from users who probably weren't even deliberately targeted, and so this is something you have to watch. You may not be the one being targeted, but you can suffer some problems. I'm not going to go through the full details of this slide. It's a real-world example that was in the NASA's callback ASRS publication, but it's an example of where GPS interference from a military exercise, a nearby jamming trial, caused widespread GPS outages. And these outages started to affect many inbound aircraft to this airport. And one aircraft that had experienced problems thought their systems had recovered and then was observed by air traffic controllers to be straying off course. Now, actually, it's quite fortunate that this sort of event happened in the aviation sector because, commercial aviation have been conservative in adopting GNSS. They've got a variety of built-in redundancy with backup radio aids on the ground, a robust air traffic control monitoring system. So there was no tragedy. The aircraft was directed back onto the correct path. But it does show you the unwanted, unexpected impacts that GPS interference can have on our transport systems. It highlights the need for robust systems. Going away from GPS interference, sometimes you get other types of threat. This was one that happened in April 2019 was when it first started happening in significant numbers. This event actually happened in April 2019. It was what we call a GPS weak number rollover event. Older GPS receivers have a weak number encoded in the 10-bit field. In other words, they're only 1,024 weeks before the value resets to zero. And you really don't want to be around any dependent systems when that value resets to zero. Legacy systems which have never, ever had a software or firmware update or never been replaced by newer equipment suffer the consequences. And we're still getting reports of these coming in now because the smart software engineers programmed that 1024-week count to start when their product was released. So we're going to see more instances of these problems. In this case, the New York City wireless network was impacted, and that caused significant transport infrastructure problems. So again, there's a message for anyone involved in the transport sector. And I often get asked, are GPS interference events on the increase? It's a difficult question to answer because the intuitive answer is yes. But it's difficult to get that quantitative evidence to back that statement up. I wondered whether it was worth looking at the NASA's Aviation Safety Reporting Scheme. So I downloaded and analyzed all of the received incident reports relating to GPS. And where the incident was clearly linked to GPS interference, I plotted the results. And here they are, the results since 1997. And I think they speak for themselves. I also think the same result would be true for overall incidents related to GPS because it's not just the interference incidents that are going up, it's the increased use of GPS also means that we're coming more into conflict with interference sources as well. There are masses of interesting reports in the database. I found some accounts of weak number rollover issues affecting regional jets. There are a series of reports of significant GPS outages around Manila International Airport in the Philippines. Yes, the threats from GPS interference, and I believe spoofing too, are definitely on the rise. Probably not a surprise to you, but the people who want to deliberately attack GNSS systems are exactly, and the users, are exactly the same groups of people that attack the networks and information systems. They're well-defined classes of actor, and they all have varying amounts of resources. They range from the unstructured hackers, the people who try to defeat a GPS tracker in their vehicle, and they don't really know what they're doing, and they don't know that they're going to cause other nearby vehicles and users to be affected. Some of these actors are more structured than others. Then you've got the criminals, and they're aware of how technology can give them an edge. And then we get to the actors with the highest resources, nation states, which we've seen some examples of them. And we see from jamming in Norway, jamming and spoofing in the Middle East, jamming in North Korea, nation states have the ability to deny GPS on a wider scale and for long time scales. So a good risk assessment when you're developing a PNT system is essential. It's all about, as Mitch said earlier, it's all about profiling your system, understand its GPS dependencies. It's a very good start to do that, as is testing your system behavior against simulated or reconstructed real-world threats and repeating. Quantitative data is what leads to your good systems understanding and good testing, a good test plan. And this is key to responsible use of PNT and GNSS. And finally, I wanted to just show some of the problems we've seen in the lab with various systems, RF and non-RF related. And we've seen everything from premature implementation of leak second events, weak number rollover issues, problems dealing with GNSS interference and spoofing are common, especially with detection. Resistance and recovery issues are common. And all of these things can lead to unexpected impacts, and in a lot of these cases did, which is why we saw them. So, a good risk assessment is vital. It allows you to assess detection and mitigation solutions from a well-informed perspective, whereas not doing it leaves you and your customers vulnerable. Anyway, on that note, thank you for listening, and this is where I hand you back to Duke.
Thank you, Guy. Very, very informative. I think I know for a fact, having known you all these years, that you have a lot more examples than the 5 you showed. I think about it every time I get on an airplane, so it's a little bit scary. All right, so that brings us to our next poll. Do you have operational procedures in place if GNSS or GPS is not available? Yes, no, or I don't know. So select the one answer and hit submit. We'll go for about 20 seconds. And while we're waiting, I'll remind everybody to use the Q&A box to submit questions that we'll take at the end of the presentations today. Okay, let's see how everybody answered. So let's see. So I don't know was the largest percentage here, and no is 32.5. So almost 3 out of 4 don't have a procedure for GPS outages, or they don't know. Interesting. Thank you for your feedback there. Okay, with that, we'll move to our last presentation for today, and that is Greg Wolf with Microchip. Take it away, Greg.
Hello, this is Greg Wolf from Microchip. In this portion of the webinar, we'll take a look at some approaches that transportation infrastructure providers can take to better secure their use of PNT services as delivered by GNSS. We'll look closely at the use of GNSS visibility and threat protection, not only for improving security, but also to construct a more resilient use of PNT across all transportation operations. Position, navigation, and timing services are pervasively used across critical infrastructure. You'll see below I have a table organized with position and navigation on top and timing down below. And in the case of position and navigation, the use of PNT of the PNN, that is, it's far-reaching, from asset tracking, to fuel truck dispatching, to avoiding train-to-train collisions, to assisting vessels with their position, especially in congested harbors. There are almost endless applications and use cases for PNT services across these critical infrastructure sectors. And then common across all these sectors is the need for very accurate and precise and now very resilient timing. The private networks that all these transport critical infrastructures rely on must be very secure, and therefore the timing for these networks must be also very, very well protected and robust. As mentioned previously, there's many use cases and applications for PNT services as delivered by GNSS across all the operations of transport infrastructure. Therefore, there's lots of different users. There's lots of different devices. There's laptops, handheld devices, consoles, all sorts of different devices using the PNT information from GNSS, using it 24/7, and therefore, when you think about it, this creates a very, very large single point of failure. As you can imagine, if anything were to go wrong with the GNSS-delivered PNT services, many different users and applications will all of a sudden be affected at the same time. So within the transport operations, with so many different users, so many different applications and devices using PNT information from GNSS, there's a need to have a centralized way to monitor the health of the GNSS signal. This is what we call GNSS situational awareness. So the way to think about GNSS situational awareness, it can be thought of as a visibility dome that's constantly looking at the health of the GNSS reception across transportation operations. So whether it's an unintentional interference or an intentional threat such as jamming and spoofing, the visibility dome, basically looks at what's going on and then alerts the other users and applications that use the GNSS for PNT services to take that the signal's been compromised and therefore to take the appropriate action as needed. Now, what's actually being monitored? What's really being monitored here by this visibility dome is what we call GNSS observables. GNSS observables are live sky characteristics which are being continuously looked at, and then using detectors and intelligence, decisions are made and determination is communicated to the many users and applications of the GNSS signal. This next slide lists some of the GNSS observables. First, let's look at tracked satellite count. In this case, are the expected number of satellites in view, whether that be 6, 7, 8, or so forth. Another GNSS observable is position dispersion. Is the position data that is coming from the live sky changing too much relative to the surveyed position of the antenna? A third, phase time deviation. This is a very important one. Is the time that is derived from the live sky signal changing too much? If it is changing, how is it changing? For example, is it changing suddenly, gradually, periodically? There are varying types of attacks that can cause a phase time deviation. And in fact, we're going to show you an example later on in this presentation. Carrier to noise. There may be enough satellites in view, but are the satellites that are in view at the proper signal strength? Is the carrier to noise too low? This could be caused by improper antenna and cabling issues. In fact, Guy referred to that previously. Or is the carrier to noise too high? This may be an indication of a possible attack. And then finally listed here is RF power. RF power level threats can come in many forms. I think we're all aware of jamming signals intended to just simply overpower the GPS signal. There are small devices such as jammers that plug into a cigarette lighter. Alternatively, there are jamming devices designed to wipe out the GNSS signal over very large geographical areas. And then there are subtle jamming systems capable of instantaneously jamming the GNSS signal with the intent of getting the GNSS receiver to start tracking a spoof signal at a slightly higher power level with the GNSS receiver knowing it has been captured. So next, in the next slides, we're going to show some videos of how GNSS observables can be monitored and what that visually looks like. We're going to first show an example of a time anomaly caused by pseudorange spoofing, and then a second example, we're going to show how satellites can be taken out of view at an unusually fast rate. So I'm going to go ahead and click now onto the video.
In the following example, we are showing a time attack occurring as a result of a spoofer creating a fake signal by manipulating the pseudorange. Let's start the demo. Along the x-axis is the time of day elapsing, and along the y-axis is phase time deviation. When the attack occurs, the GPS receiver is fooled with a pseudorange solution derived from the spoofed sky signal that does not match with the data contained in the subframes that is also being received by the GPS receiver. The result is that the GNSS receiver repeatedly moves 150 nanoseconds and creates a time offset from UTC. Monitoring the GNSS observable of phase time deviation is a way to catch this pseudorange manipulation and protect against this type of timing attack.
So there you have an example of a time attack, again, where the pseudorange information was being adjusted to create that periodic movement of 150 nanoseconds. In this next example, we're going to look at a situation where tracked satellites are taken out of view unusually fast. This is, satellites going out of view is actually not an unusual condition, as GNSS satellites are orbiting and therefore coming into view and passing out of view relative to the horizon on a regular basis. However, in this example, we're going to see something very unusual. So let's go ahead and run the next demo.
This next example is of a spoofer generating a GPS signal where the satellites are dropping off at an unusually fast rate. Let's go ahead and run the demo. We see 6 satellites being tracked, and as time goes on, all of a sudden the satellites start getting knocked off to 5, to 4, to 3, to 2, to 1, and eventually all the way down to 0. So here again is another example of tracking a GNSS observable, in this case track satellite count, and catching a spoofer making an attack.
So there you saw satellites, again, were being knocked out very quickly, where the spoofer had taken control of the receiver and the receiver not knowing what's going on. So with that, we're going to move on to the second part of the presentation. And this portion will focus on timing security and the importance of timing security as it relates to securing network communications. As mentioned earlier, all critical infrastructure sectors are depending more and more on communications, whether that be high-speed fiber transmission or LTE or 5G private wireless networks. And the first point is that timing security is actually a cyber security problem. I think Mitch mentioned this earlier. And this is how it's being viewed. It's, in fact, on the left side, this is a recent publication that Mitch mentioned earlier from DHS. And in fact, there are other initiatives from DHS, specifically from the Science and Technology Group, which will be publishing a Resilient PNT framework document that is the result of really an excellent collaboration between the government and private industry. This document actually defines levels of resiliency for PNT equipment, such that if GNSS becomes unavailable, alternative PNT sources can provide continued operation with minimal to potentially no degradation until the threat is passed. For example, my colleague Mitch showed some of these alternatives and their capabilities at the end of his webinar. In architecture, for building better timing security, as well as better timing resiliency, is what we call the Virtual Primary Reference Time Clock, abbreviated VPRTC. This architecture is the result of integrating together secure GNSS reception using the visibility technique previously discussed, along with atomic clocks based on cesium or rubidium technology, for example, and then trusted time distribution to build a system or solution that is very resilient to any kind of threat, whether that threat is a live sky GNSS reception or a threat through a network connection. For more details and information about the VPRTC solution, we've provided the URL, and I encourage you to go there. In fact, we just recently did a GPS World webinar that goes into details about the VPRTC solution. This slide shows how the virtual primary reference time clock can build a much more resilient timing infrastructure for transportation sectors, whether that be aviation, railway, or maritime. At the top, you'll see what has been traditionally deployed, where customers use GPS as their primary source of time and have dispersed GNSS across the entire network. This creates a very vulnerable timing architecture. Although there may be a cesium clock deployed somewhere in the network for providing backup, still various kinds of jamming and spoofing attacks can happen almost anywhere and can disrupt the network. Now, down below, we show the deployment of the virtual primary reference time clock. Here we're showing two locations where the VPRTC is deployed. You can think of it as kind of a east-west timing architecture. And at these locations, there's GNSS reception, but that GNSS reception is very well protected by a firewall approach. And that timing from these locations is distributed through the network using PTP. Now, not all networks support PTP. There's still many legacy networks out there. However, this approach still holds true for those networks as well. And in the cases such as remote locations, a firewall GPS reception can still be deployed to protect that location. The key point really in this architecture is that there's a lot less GNSS being used, and therefore a much more resilient timing architecture has been created. A way I like to think about this approach is that its virtual primary reference time clock architecture enables the use of GNSS and atomic clocks to be combined in a centralized location, and then this time can be dispersed securely over PTP across an entire network. This slide kind of is going to pull it all together for us as we get to the near end here and allow for questions from the audience. In the upper right corner, again, we see the visibility dome, which provides the situational awareness and can deliver protection to many devices and users and applications that make use of PNT-delivered GNSS. Again, the massive use of GNSS is without a doubt a single point of failure, and visibility of observables provides the early alert, which is a big part of constructing resiliency. The same GNSS firewall visibility is also part of the virtual primary reference time clock shown down below. And this enables the operation of a private secure network, whether it's for aviation, railway, or maritime, to have much more resiliency. So there's two key things to be taken away here. The first part is the GNSS visibility for protecting the P and the N, if you will. And then the second part is the virtual primary reference time clock, which provides the protection for the T, the timing that's needed for the underlying communication networks. So this complete solution then can also be unified with a common management system so that an operations team for an airport or for railway or for maritime can have a common view of PNT health. So to summarize, we begin with Mitch providing a top-down view of the importance of PNT services in the transportation industry. That this goes beyond protection of day-to-day operation. It's also a matter of public safety. Next, Guy from Spirent provided some evidence, some very, very good evidence from across the globe of the types of threats and the impact that these threats can have on transportation, whether it's land, air, or sea. I think Guy made an important point there at the end that that our philosophy needs to be to trust but verify when it comes to the use of PNT delivered by GNSS. And then we ended our presentation here with an approach of how we can create and use a visibility dome to provide an early alert of threats, and then using the same visibility dome as part of a solution which incorporates atomic clocks and trusted time distribution to secure communication networks is used by transport operations. This is what we call the virtual primary reference time clock. With that, I've completed my portion of the webinar. I appreciate your time, and we can, I think, now turn it over to Duke for questions. Thank you.
Thank you, Greg. Nice presentation. So we will move to the Q&A. You still have some time to enter questions in the Q&A box if you would like. But I have some early questions in here. So I'll ask the question. So the first question here will go, I think, Guy. The question is, protecting the access of civilian airports against commercial drones may require GNSS jamming, creating perturbation or congestion in the civilian airspace. Is it possible to jam effectively a drone without impacting other GNSS users?
Hi, that's a very good question, Duke. Thanks. Well, I think some of the incidents I talked about, in fact, show that it probably isn't. If you try, some of the incidents in Moscow and the Black Sea may have been a kind of drone protection system to stop a drone overflying a sensitive area, and they affected lots of innocent users. Also, if you accept, and it does seem that disrupting a rogue drone's GNSS systems is a good way to disable it and maybe bring it down, you have to wonder, what about the collateral damage to airport infrastructure and also the honest UAV or drone operators nearby? UAVs are going to be used by the Fortune 500 companies greatly, and it's going to revolutionize our environment in the next few years. So we have a conflict of interest there. On the one hand, robust and resilient PNT for the innocent users. On the other hand, the need to bring down rogue drones.
Okay, thank you. Next question. For Mitch, could you explain how and where GNSS is used at airports and what is dependent on it? And are there any requirements?
Well, that's a great question. So talking about the air operations side, certainly the FAA has done a tremendous job over the last years of overlaying and also designing and making available both approaches and missed approaches to airports based on GNSS. In fact, Part 91 general aviation is allowed to fly with GPS sole means. I certainly wouldn't recommend it, but they certainly can. So GNSS, both plain vanilla GPS and WAAS enabled, is available in many places. There's a couple of airports that actually have GBASs, Newark in New Jersey and Houston, and just using Newark as an example, they were able to accept traffic from the south into Newark, which they couldn't do previously because the LaGuardia airspace pretty much butts right up to the airport in New Jersey, and being able to use GBAS to fly under the LaGuardia airspace and arrive at Newark has really significantly helped. But if you think about the airport infrastructure, it's not all about moving airplanes. I mean, just about everything, communications of information is dependent on GNSS PNT. So you've got, like everything else in this world, a lot of stuff is networked. Audio communications, digital communications, video. When you mess with GNSS, the problem is that you're messing with a lot of services. The good news from the aviation side is there's a tremendous, robust ground-based infrastructure out there that airplanes are still using to fly. ILSs for approach and landing, DMEs and VORs, and even NDBs out there. But those systems are extremely old, and many of them put in the 80s and 90s. And I'm certainly hoping that folks do something quickly to replace that aging infrastructure, because it is what makes the system resilient. I hope that answered the question.
Yes, thank you, Mitch. Next question is for Greg. Is an independent ground-based timescale the solution for critical infrastructure synchronization?
It's an interesting question, and it's a question that I think a lot of countries, in fact, across the globe are addressing and actually taking action on now, because they see PNT as, you know, a very important national utility, and not all countries obviously can afford to launch their own, you know, GNSS system. So as an alternative, many countries are in fact putting in now and many others planning a ground-based timescale system to support their critical infrastructure. It's what we see happening in many cases is metrology labs, which would have a timescale system for doing special measurements. We're seeing that become more of a national distribution for time that's used by other critical infrastructure within the country, whether it's a telecom network or utility grid or transportation infrastructure. So the answer to the question is definitely yes.
All right, thank you, Greg. Here's another one for Guy. How real is the threat of GNSS spoofing against commercial airplanes?
Well, I think this is a good one for Mitch as well with his experience. I mean, like I said, I think you know spoofing is a threat to any unprotected systems. When people talk about aeroplanes and commercial aviation in particular, I think we have to remember commercial aviation, as I said, has been very conservative about adopting GNSS, and although they're making greater use of GNSS, they're very, very familiar with the vulnerabilities of GNSS and the risks, and they're deliberately keeping, you know, backup systems, ground infrastructure, robust air traffic control systems. There's a lot of protection now. I feel safe getting onto a commercial aeroplane. I think it's other sectors that aren't as well protected and haven't considered the risks as much, where we're likely to get the bigger problems.
Yeah, I would agree, Guy. I think the danger in GNSS is because it's so good. People tend to believe what it tells them without really thinking about other things. The nice thing is pilots are trained to trust their instruments, but if the only instrument they have is GNSS, that's a problem. I heard an anecdote. I can't tell you exactly where or when this happened or who did it, but there was a story of a pilot who believed they were flying due south, and they proceeded to do that into the setting sun for a half an hour until they realized, wait a second, the sun doesn't set in the south. So sometimes you really have to use all the means at your disposal. The mariners always like to say this: use all your navigation means in order to facilitate your operation, and don't just rely on GNSS. Cross-checking is really remarkably a boon to the outcome. And I like to tell people, you know, GNSS is really a precise system, but I'll promise you any precision if I don't have to tell you what level of integrity I'm providing. So trust but verify.
I like that, trust but verify. Stay with me, Mitch. I got another question for you. What is being done in the USA for monitoring GNSS interference at airport, if anything? And which agency would have responsibility?
So with a lot of questions, it depends. So if we're talking about aviation frequencies, certainly if there's an interference to aviation frequencies, the FAA, it does have spectrum engineering folks who go running around and try to seek out the sources of interference. We've seen wireless cameras that come in from certain countries where they're set up to operate on DME frequencies, and it's really quite interesting. But certainly FCC has the ability to monitor, and Homeland Security and DOD is certainly monitoring. When we had the interference, for instance, against the GBAS at Newark, that was a concerted effort that included the FAA and the FCC, neither of which, by the way, have police powers, and also federal marshals and local New Jersey state troopers helped as well. So when something like that happens, the good news, and I can't say this more strongly, is aviation is one critical infrastructure sector that maintains significant resilient PNT capability and intends to do so, and I can't wait for the next generation of solutions to get out there.
Okay, all right. Looks like we have time for maybe one more question. I'll just throw this one out as a toss-up. Each of you could weigh in if you want to. It's how much does the Legato 5G project a threat to PNT?
Everyone's hesitant to answer that. It's certainly a big question, and certainly there's been a lot of talks and presentations on that subject. I'm going to answer it this way, and I think that I'm going to go back to the presentation there a little bit in this concept of visibility. I think a lot of our answers to a lot of our problems lie in visibility. As they say, knowledge is power. And I think that the more that you know, the more that you can see what is actually happening, the more problems you can solve, the more ways that you can prevent interference from occurring, whether that's Legato or whether that's an antenna poorly installed or some threat like Guy talked about. There's so many of them out there. So the answer to me lies in the visibility and being able to see what's going on and collectively and as an industry, sharing what we're seeing and making sure that GNSS is delivering what we expect it to deliver.
Okay, all right. Well, thank you, Greg. I think that brings us to the end. We have a lot more questions. We'll try to answer as many as we can offline individually, but thank you for your participation today. Thanks for taking part in the polls, and thanks for the very intriguing questions. With that, I'll turn it back over to Kelly for a wrap-up.
Thanks, Duke. And thank you again to our speakers for today's informative presentation. I hope you all have enjoyed today's webinar, The Need for Resilient PNT Services to Ensure Safe and Secure Transportation Infrastructure, brought to you by GPS World Magazine and our event sponsor, Microchip. If you have any additional questions for our speakers, you can reach out directly via the email addresses you see on the slide now. Additional materials referenced in today's presentation are available to you via the Resources panel on the right side of your console. The Resources panel also houses a PDF of today's presentation slides, which you can download. A recording of this webinar will be emailed to you tomorrow and posted at gpsworld.com/webinars. Upcoming webinars from GPS World will also be posted to that page. All right, well, thank you all for attending. We hope you all will join us for another great webinar.